This is our special edition meeting, or the last meeting before the Atom series continues. Today we got some pretty cool talks. We got 5 talks from 5 PhD students. All of these are PhD students in CEFCOM, which is one of the security labs here at ASU. CEFCOM is one of the labs that kind of specializes in binary analysis, which is very relevant to the ASU Hacking Club because it is kind of what we're all built around, which is analyzing programs that have been, compiled already, reverse engineering, binary exploitation, stuff like that. CEFCOM is probably the most active lab here at ASU that does that. And so we got some pretty sick CEFCOM people, many of whom are also shellfish people. So it'll be pretty awesome stuff. As for club announcements go, we wanted to give a big congrats to the 2 people who made it into the membership listing, the official membership listing, which is Icon and at XOMG. Both of you guys, congratulations for making it. You guys were the most recent members to pwn the server and make it in. So congrats, you guys are killing it. As far as CTF goes, there is no CTF this week, but we expect to be playing a CTF in 2 weeks from now. So weekend after this one, or 2 weekends from now, I guess. We'll announce more about that in the channel as we get closer. And that's about it. Sorry. We got one other thing. The end of the semester is coming in about 4-5 weeks. And so we're getting ready to give out some awards for the top of the scoreboard. Right now, the thing we have planned specifically is for people who have gotten the membership. You'll be getting a membership item. And it'll be kind of a surprise. We are seeing if we can get it before Christmas, before we all leave for Christmas break. Otherwise, you'll be able to get it when we get back. This membership item is likely going to be a membership coin, like a DEF CON coin, if you've ever seen one. But for the ASU Hacking Club, if you become an official member on the member listing, you get the member coin. You can get it at any time between the start of the school year, so back in August, all the way till the end of the school year in May. So you could use your Christmas break to maybe figure out how to become an official member. And that is it for announcements. Anything else? Redgate, any announcements, or any of the other officers? Nope, I think we're good then. All right, so I will briefly intro the first speaker. Klasm says he also wants shirts. Nice, yes. I'll introduce the first speaker, which is Will Gibbs. He goes by Klasm on the ASU Hacking Club. He's one of the admins. He's also one of the elite people on Shellfish. He is the Shellfish captain. So he is a pretty elite guy. He does a lot of binary stuff. The first talk, which is done by him, will be on static analysis with a specific view on finding vulnerabilities. Static analysis being one of the most common ways to look for vulnerabilities in the modern day. Will be giving us a brief introduction and demo of the kind of modern static analysis stuff we have. And on that, I will pass it over to Will.
Perfect. Wrong Discord, by the way, but we're all good.
Nice.
Let's see. All right. Can we see my screen?
Yes.
Cool. Okay, yeah. So today, guys, I'm going to be talking about static analysis. So Zion gave me a nice intro, but I'll do it again just in case anybody missed. I'm a current captain of Shellfish. Most of the time when I play CTF, I attempt to solve pwn challenges. Attempt being the key word there. I'm a current CEFCOM PhD student. My current research is reaching definition analysis. And I'll talk about and give a demo later in the talk. And if you want to know more about me, you can visit my website, which I posted here. Cool. So the first topic is, what is static analysis? It's a very broad field, but very active as well. And so 2 things that you guys might be familiar. One is something like CodeQL, which is a source code static analyzer. And it's something that'll look over your source code that you've written and try to identify any sort of vulnerabilities that exist in it. And a second type is a decompiler. In this case, we have anger management that I'm showing, but there's plenty of other decompilers out there, some better than others. But right now, the kind of reigning kings are anger management, IDA, and binary ninja, each with their own advantages and disadvantages. So how does static analysis work? And so really we have to break it down, or one of the main components of it is CFGs, and that's not context-free grammar, which some of you guys might be familiar with, but control flow graphs. And so here's an example of a control flow graph. So we have some source code, there's some loop in there, some if statements, else statements, whatever. And you can see on the right, we break it up into its composite CFG, where you can see all of the blocks of code are labeled with a number 1 through 9. And then the CFG takes those nodes of those blocks and shows you a graph into how they're all interconnected with each other. And so this is kind of the bones of static analysis, or many static analysis tools. But the difference is when you don't have source code, like if you're using a decompiler, right? Then how do you make up the CFGs? Well, first we have to start with something called basic blocks. So basic blocks is because you have a binary, right? You don't have source code, you have to use the disassembly. So basic blocks takes that disassembly and you break it up into different control flow chunks. So you see on the previous slide, wherever it's broken up to, where there's while statements, loops, ifs, any sort of type of control flow where the program can, there's some sort of decision that needs to be made as to where the program will continue to. And so basic blocks are the exact same thing in assembly code, except instead of having the nice source code, the if and else statements, we would look at jumps, and that's pretty much the core of it. There's jumps, there's calls, and there's return. You can see I have all three here, and those are the things that kind of transfer control flow. So a CFG, I'll show you guys right here, is kind of just an amalgamation of all of these different blocks put together. So let's see, can we see that, Zion, or is that hard to see?
Yeah, that's kind of seeable if you look close.
If you look close, okay. Give me 1 second. Yeah, it'll be fine. It'll be fine. I'll continue with the presentation, and then I'll show you guys a better example of a CFG later down the line, or maybe this exact same CFG, just better readable. So anyways, so static analysis takes these basic blocks and turns them into a CFG. And so why are CFGs important? Well, CFGs are what is needed for all other, or is what all other types of analysis are dependent upon. So here's an example for you guys. We have some nice taint tracking here. So taint tracking, this is, in this case, is static taint tracking. There's also dynamic taint tracking. But essentially, you take, we can see here our W equals source. You take some source, and you try and find all of the sinks that are connected to this source. And so this is the reason why CFGs are important, is you have to go from each step of the control flow and try and figure out where is this variable going, right? And if you follow the arrows and the numbers labeled here, you can see we start from our source inside this function foo and end up in this labeled sink function. And so taint tracking isn't just, it's, why would you want to do this? Well, one example is, let's say that you have some sort of input that you can give to a program, right? Let's say you have some gets, some f gets, some cin, whatever type of input or file that you can give to the program, and you want to see, does this go any place that I care about? And so that's where something like static taint tracking could potentially be useful to you guys. And now we have another really cool example, which is binary rewriting. So binary rewriting, and this is pulled from a paper called Rambler, which was a great paper written by one of our professors, Fish, as well as many other great co-authors. So Rambler, so let's say you have a binary, right? You no longer have source code, but you want to make a patch to it. You find out that, hey, this thing's vulnerable. You don't have access to the source code, which for some reason, either you lost it, it's difficult to obtain, or it's an older software, and the legacy code is unusable or untenable. And really what you want to do is you just want to make a small, tiny patch. So that's actually almost impossible to do directly with regular binaries. And the reason that is most of the references to hard-coded data structures, like you can see in here, we have the string of option A, option B, unknown option, and then we have the global variable of counters. Those are all going to be normally referenced based off of the current offset of the instruction pointer. And the reason that makes it difficult to apply these patches and rewrite them is that if you add any sort of code before that offset, you then change the location where that exists, or the difference from the offset. Now now it doesn't exist at 60 bytes plus the instruction pointer. Now it exists at 62 bytes plus the instruction pointer. And so what Rambler does is it takes this disassembled code, it analyzes it for all of the pointers and all of these different types of offsets, and then converts them into essentially a type of symbol that can then be used to insert your patch that you want to insert. And then it recompiles the binary and re-puts in the offset with now the correct offset. And this is totally impossible without having any sort of static analysis, because pointers are a little bit more unwieldy than one might like. And now we'll come to my current research, which is reaching definitions analysis. And so reaching definition analysis, if you look at the taint tracking that we have here, right, we start with a nice source and we see, hey, from here, where do we end up? Well, reaching definition analysis can actually work in kind of the opposite way. It's, hey, we have the sink that we like, which in this case, I'm giving you an example of this mem copy. Hey, we have the sink. We want to see, is this, where does this variable get instantiated? Like, is this along any sort of route that we actually care about? And you can see I stole this nice slide from Purdue of exactly kind of what we're talking about, right? So you go from, you kind of work your way back up. So you're like, hey, this return, which is this is a less than n, where does this a variable actually come from? Where does this start from? This starts, you look directly above it. You say, hey, a is b times 2. Okay, great. Where is b times 2? B is actually of this second function here, which is equal to a plus 1. And then, okay, where's this definition of b? Or where's this definition of a? And you have a equals 0. And so now you know exactly the value that is supposed to be compared in that a is less than n. And so my current research, which I'll give you a demo in a moment here, but my current research kind of implements this, and in a way that is easy to use, so that users can try and figure out, like, hey, is this function that I care about reachable from some other places? And I'll give you a nice little. Can we see anger management?
Yep.
Cool. Okay, so cool. So let's say, so this is anger management. This is the decompiler. This is something that I showed you guys in some of the beginning slides. I've loaded up kind of like a toy program here, but let's go into one of these functions, and I'll actually decompile it so you guys can see it. So we can see in this function, all that happens is we have a sprintf where you're like, okay, you have some sort of string, and in that string you get the %/ inserted, and then, oh, look, you have system, and system calls this function, or calls system with this string. And this is all this is going to do is list out your home directory, right, with some sort with the options for all and in a nice list. So let's say we see systems called here. Let's see if we can figure out if systems used anywhere else. Oh, does it not like this? Depends. Okay, there we go. So this is currently, it's a little janky, but for research purposes. So we have system here. We want to analyze, hey, this first command, this first string that gets in here, is there anywhere that this is defined where it's actually interesting for us to use? And so we hit OK. And so now we have, you can see we have our initial call here with system. And forgive me, some of these lines are a little messed up. But we have our initial call to system here, and we're like, OK, where does our first argument come from? And you can see we take two paths immediately. This bottom one was the function that we were in, this resolved. Which if we follow this, all the way back, all the way down over here, you can see it resolves to our string of ls-alh %s. And you can see that this then comes down into, where is it? A sprintf with another argument. And you can see that this %s, right? It gets resolved. And you can actually also see the other argument to sprintf here, which is our %/. And you're like, okay, we already understand this. We already know this, But then what's our other path here, right? We have this unresolved function. Or the function's name is called unresolved, right? We have a sprintf, exactly like the sprintf over here. But the arguments to this sprintf, we can see, hey, we have this ls %s, right? So this will execute your ls command with whatever the second argument is, sprintf. And then you can see that the second argument to sprintf is actually unresolved here, right? We can't actually trace it back to a hard-coded value like we can here. And so if we double click on this, right, we can see, oh, here's that ls sprintf. Here's our system. And then if we decompile, you can see that, oh, the value that we're sprintfing is actually the register that's passed in, which is the reason why this was unresolved.
Hey, Will, you might want to zoom in a little.
Oh, no.
Yeah.
We liking that?
Yep.
Okay,
much
cool.
better.
So okay, so here's your RDI. Here's your, which if we go on the dependencies, it tells you exactly that, hey, this starts from, I can't highlight it. This starts from RDI and it gets loaded into our offset of base pointer, right? Just like normal, like you would expect. And so, okay, here's our unresolved function. And we know that we have RDI. Where's our, oh, does it not like express? Can I only do it here? Okay, where's this called? Oh no, okay, here we go. And like, oh, look, unresolved is called from this function, which is put in this A0 field A. And really what this is your argv. I think anger management is doing some weird stuff here. But so you can use this to determine like, hey, we have this sync, we have this system call. Where does this go? And you can do this so it doesn't have to be specifically for system, but you can do sprintf as well. We can do depends on, and let's say we want to do argument 1. And then you can do the exact same thing that we did for system for sprintf. And you can see the exact same thing that we have here where we have the two different values, except it's not able to resolve the other hard-coded value of the we're not resolving the other hard-coded value of the home string just because we're only looking at the first argument of sprintf. So anyways, this can be used. So this is nice and relatively simple for users to use, but this can also be automated. And that's actually the focus of my current research, is taking this ability to say, hey, there are interesting syncs, right? You have system, you have execve, you have other types of functions like sprintf that have, interesting operators in them that you might be able to use maliciously. Let's take these and can we try and detect these automatically? And of course, the answer is yes. And so that is the current focus of my research. So if we go back to static analysis, cool. So with that demo over for you guys, let's talk about some of the limitations of static analysis real quick. So first of all, static analysis. So we saw that was nice, but static analysis isn't actually foolproof yet, right? There are a couple cases in which it's faulty. One such case is with virtual tables in C++ or indirect jumps. Like if you're jumping directly from a register, like jump RAX or jump RDX, something like that. It's actually difficult to resolve through pure static analysis alone where that will jump to, right? You might be able to narrow down the range, but and some place where this is easily visible is switch cases. But you might be able to narrow that down, but a lot of current decompilers and disassemblers don't actually have this functionality 100% built in. I'm pretty sure that Zion's doing some research on this, but that's yet to come. And then the other thing is that we can't model data like dynamic or symbolic analysis, right? Like we saw the steps of the program, we saw all of our arguments that could be there. And this is the reason why reaching depth analysis is powerful, is you could see the hard-coded strings in there, right? We saw the ls%s in there, but we can't really model the other type of data in there, right? It's possible that, you know, from our own analysis, we could look and see that, hey, this actually comes from argv, but it's possible that there's other constraints that are put on that data, right? Like, let's say it can only be a certain length, or it can only contain certain characters, or some characters are filtered out. That can't really be done with static analysis alone, right? That has to be some sort of combination of static and symbolic or dynamic analysis, which I'm pretty sure some of the other presenters are going to be touching on. So real quick summary for you guys. Static analysis is built on CFG recovery, which is built upon basic blocks. The principle behind it is relatively simple, but is complex to execute in practice. Static analysis is a broad field with active research and improvements being made every day, every conference, all the time. I just gave you a few examples, right, which were taint tracking, decompilation, RDA, the binary rewriting, but there's plenty of people that do really, really cool things all the time. Static analysis comes with several limitations, which is the, I mentioned, but the inability to track down indirect jumps, as well as the inability to model data. And finally, I'm awesome, and so are you guys for listening to this. It's cool that you guys are interested in hearing about this, and hopefully you've gained something from this talk. At the end here, I've included some links to some of the stuff that I talked about, including the Rambler paper, which is a cool read. So if you guys want to go through those, I'm pretty sure we can post that later. Thanks, guys.
We'll take some questions now if you guys want. We got some questions in the Twitch, which I'll relay to you if people give new ones. So we'll open it up to questions for a second if anybody wants to ask Will, the static analysis master, about static analysis. Any questions? Last call for it too for the Twitch. How is taint tracking? Okay. One question is, how is taint tracking done currently in Anger? I guess he's kind of asking, how does it work in Anger?
So I think this is more. So I think Anger's taint tracking is really dynamic instead of static. Although I'm not 100%. Let's see. No worries, dude. So anyways, so in Anger, really, Anger is super powerful. And so it's much easier, instead of trying to to get the results that you want, instead of trying to implement or use taint tracking in Anger, is to use Anger's ability to symbolically execute the program, as well as insert symbolic variables to figure out what your potential output could be from a sink to a source, or source to a sink, sorry.
Nice, awesome. We have a question from Jude in the Zoom. Does CFGs get built by people or programs?
CFGs for sure get built by programs. I'm sure you could build a CFG by hand if you really wanted to, but it's really, CFGs are kind of just undoing the work that the compiler did a little bit, right? So it's kind of it's deterministic up to a point.
All right, and then the last question is backward slicing used in the taint/sink tracking?
So for taint tracking, backward slicing, I do not believe is used, as it's like a forward operation. But during the CFG construction, I'm pretty sure that backward slicing is used to help fully construct it. Although I think
I say it is used for the switch cases, for resolving switch cases. It's used. Backward slicing is, but normally I don't think we use it, right? I don't know any other uses that we do.
No, yeah. Well, I think backward slicing is like purely a CFG thing, right? Like like taint tracking is pretty much just a framework built on a CFG, if that makes sense.
All right. Awesome. Thank you, Will. That was great. We'll now be moving on to the next topic, which will be by Ashwin. Shucks, we missed a question. Maybe we can get to it later, or maybe you can answer in the Twitch, Will. There's a Twitch question.
Yeah. Make sure to not reveal my username. It'll be fine.
Awesome. All right. So now we'll be moving on to the second speaker of 5, which is Ashwin, another PhD student at CEFCOM, as you probably guessed. Ashwin does work in static analysis similar to Will's, but Ashwin's is more considered for obfuscation and deobfuscation. As you probably know, obfuscation is a technique people use on binaries to make them hard to understand so they can't be reverse engineers. Sometimes this is on normal software, sometimes this is on malware. And a big research topic is how can we deobfuscate things automatically or without much user input to make things more understandable. All right, Ashwin, take it away.
Hi, thanks for that introduction, Zan. So my name is Ashwin, and I'm a PhD student in CEFCOM, like all the presenters today. And I'll be talking about obfuscation. So can anyone guess what this program does? Just type it out in the Zoom or Twitch chat. And it looks pretty hard, right? But this is a program that simply prints hello world. And I got this from the International Obfuscated C Code contest, which is this contest where people just create crazy obfuscations, and not really practical obfuscations. I'll let you know what that means, but like just cool obfuscations. So check that out if you guys are interested in seeing some really crazy stuff. Here's another interesting obfuscation, which is called the movefuscator, I guess. On the left is the program, which is the input, and on the right is the obfuscated program. I'm pretty sure the image on the right is pretty blurry, but I'll tell you what it is. Basically, every instruction on the left-hand side is converted to a move instruction, to an equivalent move instruction. So all the instructions on the right-hand side are move instructions. And this makes it extremely hard to reverse engineer. But it also comes with its overhead, performance overhead, right? So this is another cool obfuscator. So let's talk about who uses these obfuscations. There are many uses for them. So one of them are malware authors, because it just takes more time to reverse it. So it's something that I think most malware authors would go use. And that the malware can stay active for a longer period of time. And then if you are interested in protecting your intellectual property, then you will definitely want to obfuscate your code, right? Let's say you are Adobe, a company like Adobe, and you have this new algorithm that does like amazing, that generates amazing images, or like does some crazy stuff, and you want to like keep your algorithm secret. You just obfuscate your program. And then commercial softwares like Snapchat and Microsoft also use, and other companies that make games obfuscate their programs so that it's harder to crack it and reverse it. And note that it's not impossible, it just makes it harder. That means it takes more time. And this time is what sort of gives the companies usually the advantage. They can develop more features, fix more bugs, and that way customers are sort of, convinced that it's better to actually purchase the original software because of the better features and updates than compared to the cracked one. Yeah, and then embedded devices. These days, there are like a lot of embedded devices out there. So, and the code basically is in the hands of the customer, so they are free to do whatever they want. They can reverse it and understand the logic and basically steal proprietary technology if they want to. So some of you might be wondering now, why not obfuscate all programs? If obfuscation is that cool, like why not just do it to all programs? Then the thing with obfuscation is that, first of all, it does not guarantee security. It only buys you time, and also it's extremely frustrating for attackers to reverse the obfuscated code. And the second thing is that obfuscations are not free. They definitely affect the code performance in terms of either time, energy, or memory consumption. And depending on which of these parameters is valuable to you, you would want to use those particular kinds of obfuscations. So you need to be very careful with what kind of obfuscation you apply. If there's a code that needs to run really fast, you should not be using obfuscations that are extremely heavy in terms of consuming time. You can't have your customers waiting for an hour for a game character to move after you press a key. And there are also some research. There's also some research done in the energy consumption and memory usage when it comes to obfuscation in embedded devices. So yeah. Here are some examples of obfuscations. So there are many different types of obfuscations. Like, there are a lot, and I'm only presenting a few of them here. And you can also come up with your own obfuscations, right? Like, there doesn't have to be some thing that's already out there. You can easily come up with your own stuff. So the first type of obfuscation I'm going to talk about is mixed Boolean arithmetic, which is basically bitwise arithmetic, right? So here you can see that x plus y can be written as this expression on the right hand side. So in your binary, you can essentially replace all addition statements with this bitwise arithmetic on the right hand side. And this will obviously make it really hard for a reverse engineer to understand what's the actual logic of the program. And if you know about symbolic execution, it also sort of is hard to symbolically solve mixed Boolean arithmetic. Then we'll talk about opaque predicate, which is, it's basically a function which always evaluates to true or false, and it's only known to the programmer. So it's known at compile time, and at runtime, it always evaluates the same value. So for example, here you can see that this condition is basically 0 for all integers, right? And this is something that only the programmer knows, and the reversal can find it out with some time. But at the end of the day, that's the point of obfuscation, is to waste the reverse engineer's time to a point where he eventually gives up. And the third one is the data obfuscation. One example, there are many kinds of data obfuscations. One example is to use a custom string encoding that makes it harder to sort of read strings in the binary directly. Often you might have played a CTF and you're trying to reverse a binary. First thing you would do is try to correlate the program's output strings with the string in the binary, right? You'll like try to go to the string section in IDA and you'll try to see if the same strings are there. But if the string is encoded, it becomes much harder to find that correlation. And then very simple obfuscation is to just replace sequence of instructions with like much more complex instructions. So the example of this is obfuscator, the one I showed in the beginning, which replaces every assembly instructions with an equivalent set of move instructions. Yes. So then there is control flow obfuscation. This is the kind of obfuscation which tries to hide the control flow of the program. And as Bill talked about, CFG sort of gives you an idea of how the control flows through the program, right? It tells you which basic block is executed next. So one form of obfuscation in this is called control flow flattening. And if this on your left-hand side is your input program, which sort of has a normal control flow, right? Like it basically tells you after this red basic block, the green and the pink one are possible. But after you flatten this program, you sort of don't know, like it basically just shows that after red, any of these basic blocks are possible, right? And how this is implemented is that there is a dispatch variable which sort of guides which block is going to be executed next. And that's in this red basic block. So that variable tells, okay, this is the block we're going to execute next. And after that, it's this and this and this. And something in the same family of control flow obfuscation and control flow flattening is a virtualization obfuscation. It is very similar to control flow flattening. I will talk about how it is different in the next slide. I mean, the slide after this, I guess. And then there is dead code insertion, which is simply inserting instructions that do nothing. They just are there to confuse the reverse engineer. You can just insert junk sequences, right? And they don't change the semantic meaning of the program because they don't really do anything with the user's input, right? So if you were to do taint analysis, you would see that the input never really touches these junk instructions, or even if it does, it never really modifies the semantic of the program in a meaningful way, in any way actually. So here on the right hand side, there's an example where this is a snippet from a VM Protect 3 protected program. VM Protect 3 is a commercial obfuscator which virtualizes your program, which uses the VM Protect virtual machine obfuscation technique, about which I'll talk later. So on the left side, you can see that there are a lot of junk instructions, and on the right hand side, you can see the same set of instructions after we have removed the junk instruction. This work was done by one of our interns who is also an undergrad in ASU, and his name is Mitch. Yeah, very cool stuff. He has a blog where he wrote about how he reverse engineered these commercial obfuscators. You can, I'll put that link later. Okay, so let's talk about some deobfuscation techniques. So the thing with obfuscation is that every form of obfuscation requires its own specific form of deobfuscation or technique of deobfuscation. So there's no one generic technique that works on all. Let's take the example of the obfuscator. How would you go about deobfuscating it, right? So the way obfuscator works is it sort of converts each instruction to a move instruction. So if you can sort of pattern matching and go back from the set of move instructions to a single assembly instruction, that is one way of creating a deobfuscator for the move obfuscator. And it also works for sequences of code like this one, where you can see this. The first instruction is add EAX, 1, add EAX, 2. Can be simplified to add EAX, 3. So for these kind of simplifications, you can just write simple regular expressions that match and replace the instructions. Then static analysis can be used, where you can just look at the control flow and try to manually figure out what's happening. Problem with this is that if there is a dynamic or an indirect jump, it's hard to figure out where it's jumping, and often the control flow is context insensitive. So for example, in control flow flattening, we saw that when you look at the CFG, you cannot really figure out which block really comes next after the first one, right? Then we have dynamic analysis. So dynamic analysis does not have the same problem that static analysis has in terms of control flow flattening. You exactly know which block comes next after a certain block. But the problem with it is that it's not complete. You can only see one particular path that the program takes with respect to the input. So you will have to give different inputs to see different paths a program can take. So one good idea is to use static and dynamic analysis together to build your knowledge about the program and all the paths it can take. Then there comes symbolic execution. Symbolic execution. So Arvind is going to talk more about symbolic execution, but I'll just give a brief explanation of how it can be used. Symbolic execution can help us give semantic meaning to the program. Basically, it runs the program assuming you're given variables instead of concrete values, and you can use these variables to simplify complex expressions that come up. Yeah, I don't want to go too deep into that, so I'm going to skip that for now. And then taint analysis works really well because you can see which input instructions have been touched by the user's input, and we can say that those instructions are definitely relevant and the others might not be. So in the previous example that we saw, we can use taint analysis to see exactly which instructions are not junk instructions in this one. And there are loads of custom tools out there that are built specifically for certain obfuscations or certain obfuscators. But there is no generic tool that works for all of them. So that's why you might have seen that whenever you're playing a CTF and you come across certain obfuscation, you usually have to build your own, script or tool to do that at that point of time, because also for a CTF, they usually come with their own handmade obfuscation, so it's much more harder in a way. Yeah, and so my research, I work on virtual machine-based protection, and what is that? So it's a form of obfuscation in which, let's say, you have a program you want to protect, right? So we create this virtual machine, right? We write a program which is a virtual machine that understands and executes your custom instruction set, which is secret. So only you know about that instruction set, right? So, and then you convert your original program, let's say it's an x86, Intel x86, you convert that from x86 to the secret instruction set. And then you run that secret instruction set program in your virtual machine. And you basically give this whole package of the VM running your secret program, secret instruction set program as the software to the consumer or the customer, right? And the reason this obfuscation works is because when the reverse engineer opens this VM protected program, he doesn't see the logic of the program that's actually running in the VM. Instead, he sees the control flow graph of the VM itself, which doesn't really, give us much, right? It only tells you how the VM is operating. It doesn't give you any semantic information about the underlying program that's running on the virtual machine. So if you open it up, it'll look like this, something like this picture, where it's basically just this one dispatcher block and a lot of other smaller basic blocks that emerge from it. So it gives you no idea of which instruction was executed first, which basic block was first, second, or third. It just looks like this. So the control flow is flattened, and yeah. So now I will show you, I guess it's not a demo, it's more of what I've been working on so far and the progress. So I've been working on automatically deobfuscating these kind of protections. So this is a CTF binary from our CTF 2018 called Simple VM, which implements a simple VM. And as you can see, this is like the dispatcher loop, the dispatcher block. And from here, there emerge like a lot of these edges that go to many of these other blocks, right? And it's really hard to understand what's happening. So my research is trying to sort of automatically deobfuscate this to get a semantically meaningful program, right? And after I run my analysis on this program, I'm not going to run the analysis because it's going to take too long. So let's say I did run it. Now the result, I already have the results. So I'll just show you guys that. The result is going to look something like this. It's still work in progress. So these are X instructions. Yeah. So this is what the final output looks like. And I hope you guys can see this. Just a second.
Yeah, we can generally see it. Yeah. Or
okay.
Yeah, we could. It looked like you took that kind of big circular one and made it into a linear one.
Yes, exactly. So you can see that has become linear, and now you can actually tell which basic block comes after which one. So you can sort of make sense of the program in terms of what's happening. And basically the virtual machinery has been taken out, and all that is left is the underlying program that's running that you are trying to protect. So this is much more easier to understand and reverse engineer compared to this. And that is what my work has been so far. Yeah, that's my presentation. Thank you.
Very awesome. So you took that VM and turned it into some normal linear program.
Yep.
Very cool. We have any questions? And I will post that in the Twitch as well. Any questions, anybody? Feel free to either unmute yourself if you want, if you're inside of the Zoom call, or put it in the Twitch or any chat you want, and we'll get to it. All right, we got one in the Zoom call. Is this a feature you have on the Anger platform?
It will eventually be. Right now, it's very much a research prototype. I'm still working on getting it to run on as many programs as I can, and also add a few more features. But yeah, eventually.
All right. If there are no other questions, last call for questions. Oh, we got one. We got one more question. In the Twitch chat, are you using, oh wait, two actually, sorry. What do you think about cryptographic program obfuscation is the first one.
I'm not sure what cryptographic program obfuscation is. But from what I understand, as long as it's running on your machine, if you have the program, then eventually it doesn't matter, right? It's just a matter of time. Like eventually it's gonna get deobfuscated.
Awesome. And then the last question here is, are you using Python or a different language? The language question.
Oh, I'm using Python, yeah, because Anger is in Python, and I'm developing most of the stuff using Anger, so it's in Python.
Awesome, brilliant. All right, thank you, Ashwin. So we'll now move on to the next topic. The next topic is fuzzing, and it'll be presented by Gokul. Gokul is, of course, another PhD student. He researches some subfield in fuzzing. Fuzzing is a recent development in security, which is tasked with finding vulnerabilities automatically in software, and for our specific case, binaries. Fuzzing has exploded a lot in the last few years and has been a very hot topic for research. As you can imagine, finding vulnerabilities automatically interests many parties. So Gokul now will be talking about that, as we've just went from static analysis and deobfuscation, which is more about using tools to help you in general look for vulnerabilities. Fuzzing will be finding them automatically. And I will pass it off to Gokul.
Thank you so much, Zion. You did half of my job.
Yeah.
Just give me a second. Oh, yeah, there you go. Okay. I guess I can see my screen right now. Okay, all right. So my name is Gokul. I am a second year PhD student at CEFCOM. Wait a second. Okay. And then I play CDF with Shellfish. That's my GitHub handle. My interest is mainly in binary analysis and reverse engineering, and I do a little bit of web stuff as well for CDF. So currently, my research is on techniques in fuzzing, which I'll be talking about later. Going on. Okay, so what is fuzzing? So as Zion said, it's a software testing technique by feeding in some test cases into the program. And the program is monitored for any errors. Usually we call it a crash. The next one. Okay, so an example, say we have a target program and then it asks for the input. So we give a bunch of, in this case, A's, and then say it outputs whatever the input that we give. And then we try to change the length. We try to change the characters and try feeding in a lot of inputs. So this, when being done automatically by changing the length, by changing the bytes, it's basically fuzzing in very simple word. All right, so what exactly is the difference between manual testing and fuzzing? So in manual testing, what the developers would do is that they would run the target application with a bunch of inputs, usually a few test cases, and then tracks for the unintended behavior. They would have a feedback with which they would look into what the response was from the input. And the aim of this is usually to prevent users from encountering the errors. But then with fuzzing, what the people who fuzz would do is that they run the target application against a lot of abnormal inputs and then tracks for the unintended behavior. Over here, the aim is to prevent attackers from encountering exploitable errors. Right. Okay. So a few examples of fuzzers. There are like 3 types of fuzzers right now. One is mutation-based fuzzers, which does, I mean, what it does is that it alters the existing data or input samples to create a new data set. Say, for example, there is a test case or a test input saying, like, say, fuzz, and then the mutation-based fuzzer would mutate each byte or maybe all the bytes. That's what it does. The generation-based fuzzers would define a new data based on the input of the model. And the last one, which is the current trending one, or the one that is being used, is the evolutionary fuzzer, which generates inputs based on the response from the target program, which I'll be getting onto later. So what is white box versus black box fuzzing? So this is a kind of like a common term that is being used. So black box fuzzing is that feeding input to a target application without any verification of the code. So basically, you don't know what the target application does. You don't have the source. You just feed in inputs. So it can either take input from standard input, or it can take inputs as files. So you just feed in random stuff and then see what the output is. In terms of white box, you have the source, and you can verify. So with that, you can verify the code paths traversed by tracking what the input does. And you can modify the input to increase the code coverage. And for this, you can use symbolic execution, about which there is a upcoming talk regarding symbolic execution. So I'm not going into detail about that. Okay, so this is something. This is a comparison of using a target with no knowledge plus a dumb fuzzer, and the time spent and the code coverage for each of those. So if you take a target which you don't know anything about, and then you throw a dumb fuzzer at it, like say a mutation-based fuzzer, the average code coverage would be around 50%. So for a white box, say where you have the access to source and you know what exactly the input is doing, for that the code coverage is slightly better. But then if you have a smart fuzzer, then the code coverage is much more compared to the dumb fuzzer. Even when you're treating the target as a black box. Okay, so there are a few roadblocks for all the fuzzers. One is like for mutation-based fuzzer, we don't know when to stop. We can just keep on fuzzing it, and it can go on for like weeks or months or maybe years, but still it won't give you anything. But I mean, it may or it may not. So that's it's actually a roadblock. For a generation-based fuzzer, it will terminate, but we don't know when. It can take like a very long time, or it may terminate like very quickly. So what do you do for that? So the very first thing we could use or make use of to avoid the roadblock is to use code coverage, which gives you or us an idea about how well the code was tested. It is not perfect, but it is a good metric. So there are like 3 types of coverage. One is statement coverage, where we can see like which all statements have been executed. The other one would be block or branches covered. And the last one would be which all paths were taken. Okay, so one of the most popular fuzzer right now, or have been for years, is AFL, which is American Fuzzy Loop. And this was developed by a guy in Google who works at Google. And it's open source. Now, why do we need AFL? Because it finds bugs, and they have like the website has listed like all the bugs it has found. And then what can we do with it? We can just sell it for money. Like everyone needs money, so you throw this fuzzer at the target programs. I mean, I don't think right now if you do it will work, because a lot of real world softwares have been tested a lot. But I mean, there are a few programs which have like not been tested yet, I guess. So if you could throw AFL at that target program, you might be lucky to get a crash. So, and that which can fetch you some money. Okay, now why AFL? Like, there are a lot of fuzzers right now, but then a lot of people use AFL because it's really easy to set up, it's fast, and it's like it has got a decent test case generation. It has got it is open source, so you can write wrappers to make it like actually work with targets that are actually not supported by AFL itself. Usually the target program that they support is a 32-bit or 64-bit Linux binaries or OS X or like OS X or yeah, and they have a white paper as well. So you can you can read it if you want. It's not bad. They have a lot of other options as well in AFL. I'm not going to go through all of this, but it will be very good read. So I have a demo to show about fuzzing. Just give me a second. Oops. Yeah. Okay. So yeah, I hope you can see my screen. Yeah. Okay. So I have like AFL cloned. So it's already compiled and everything works. And I have a target program which is just a simple C file. So it's just you give an input greater than OX10, it would crash. Basically, you override the return instruction. So this is like a simple program. But then, like in a real world scenario where you have a huge binary, you don't know where exactly the bug lies. Or I mean, for sure there'll be bugs everywhere. At least that's. I mean, it's because we are writing the program, so for sure there'll be bugs. So for a large-scale program, it is quite difficult to analyze the whole source. So this is where fuzzing comes into play. So oops, there's a certain command for people who don't know how to use it. You can take a look at their documentation. But so this would just run like fuzz the target program with a seed that I've given, which was just a random like character, and then it would start fuzzing the target program, and then we can see the number of crashes it has found. But it's just one, but there are like a lot of duplicates, so it can basically find an input to crash the program, which is good, which is what we are looking for. So if I try to run. So there are like a few stats inside the output folder where we are pushing this or where we have to like where we can. So we'll have all these stats regarding the code covered, the crashing file and things like that. So if you run the program against so it crashes the program. So which means that we can actually, so this, what happens over here is that the input overrides the return address, and we can control like wherever we want to go. So there is a function win, which it's in the, wait, what was the name? Okay. Yeah, so there's a win function. I mean, we can jump to win. Similarly, like we can do whatever we want. I'm not going to like write an exploit for this program, but you can do that. It's just that what fuzzing would do is that it would give an input that would crash the program. But it depends. So the thing is that for a simple program like this, it's good enough. But then for like programs which require, say, if the program has say a check at the beginning to see that it only accepts like images, you need to have a magic bytes at the beginning of the file. So that is something which we have to give as the seed. Like over here, I just gave the seed as a like fuzz. That's it. but for different programs, the seed would differ. So that would improve the code coverage a lot, because otherwise the fuzzer would have to determine what the input should be, and which would take a very long time because it has to mutate and figure out what exactly the input is for each program. So that's with the demo. Yeah, okay. So talking about my research, I had shown that there were like around like 58. They said there are 58 crashes found, but just one was unique. So my research is on like finding unique crashes with like so without triggering any duplicates or like reducing the false positives as well. So regular fuzzing can give you a lot of duplicates. There have been a lot of research going on using different techniques till now, but what I'm also working on that, but I am using a different technique by rewriting the binary after finding a crash. So that's what I've been working on. It's not over yet. It's not complete yet. So once it's done, it will be open source. Okay, so as Zion said, the research on this area has exploded, and there are like 85 papers till 2020, like from 2014 or 2013, I guess. You can find the list of papers on that repo. Like so they usually maintain all the list of papers from, I guess, 2013 or something, and it's a pretty good repo. And for almost all the fuzzing papers, the core idea, like the fuzzer, the base fuzz that they use is AFL because of how robust it is. Okay. And about the summary, so we understood that the purpose of fuzzing relies on the assumption that there are like bugs within every program, which is what I said. And fuzzing can add a different view to like software testing in general. So this can be adopted by the development people as well. And code coverage plays a very important role in determining like how good or bad the fuzzer is, and also the bugs found, like the real world, the CVEs that you get by running your like fuzzer against all the real world softwares. Yeah. So yeah, that is it. And if you have any questions, feel free to ask.
All right. Yeah. Let's thanks, Gokul. Let's open it up to questions.
Yes.
Same for the Twitch stream as normal.
So when you say you're modifying the program, are you just patching out that branch that causes the crash so then you'll explore other parts of the program?
So I wish I could give out more details regarding that. So it's not exactly patching the that block. It's more about like, so you cannot patch a binary like if you can patch it. The thing is that you should not be patching in such a way that you modify the whole the flow of the whole program, the whole control flow of the program. So you need to patch in such a way that it doesn't modify it. So there are a few strategies to do that, which I do. So that's what I've been doing.
Okay.
Yeah.
We got a whole series of questions in the Twitch. I'll try to choose two and then flip back to the Zoom. First one is, can you understand fuzzing as brute forcing unknown software to find bugs?
I mean, you could do that probably, but then I don't think you would get anything out of it. So it's just that, the way AFL, like, so I mentioned AFL over here. So the way AFL works is that you could, so if the target program behaves in a way that it takes in an input from standard in, or it takes the file as the input, you could just simply, like, you can just make AFL work with that target program easily. But then if you want to make it work with, say, protocol based, like some target, you would have to write a wrapper around it to make it actually work with AFL. And then you would have to, so this is what I said. So if you give a proper input to a program, And then as I said, I gave an example of the giving input as an image for like if you want to first say a library parsing, an image parsing library, you would have to give it an input which would actually work with it. So which has to be an image. If you don't give an image, it would simply fail, right? So any fuzzer would have to spend a lot of time to determine what a proper input would be. So you cannot actually throw or you cannot actually any unknown software like that. It's always good to have. That's what makes a smart fuzzer and a dumb fuzzer. So if you can get like a deep knowledge on what it does, and you could tweak your fuzzer a bit to make sure that it works well for your target, then yeah, there you go.
Awesome. We'll flip back to another one of those questions in Twitch after, but let's take one from Sean here in the Zoom. Do you personally have a process for turning a dumb fuzzer to a smart one, or does it vary?
I personally would I personally would try to understand what the target program is, and then so the seeds or whatever the seeds that you're given will play an important role. So an example I could give you is that, say, you have a target program which had like, say, 20 or 30 CVEs reported like in the previous year. And then if you can get the inputs to trigger those CVEs on the previous version, you can put that as the seeds for the latest version of the software or that whatever that is. And then fuzz it. That might, so it will make it better, but I'm not going to say that it's going to be really better, because there are a lot of things that would depend on the word smart. It's not just a seed, but on a simple node, you could do that if you want.
Awesome. We'll do another in the Zoom. Jude asks how does AFL tell the code coverage percentage of a binary?
Okay, so you could use a tool called AFL Curve, AFL Curve or AFL Curve, which uses the test cases that AFL has produced, and that would calculate the code coverage for you. So it's not directly in AFL itself, but then you could use an external tool to do that.
I think he's more asking like how does it get coverage at all? How does it know code coverage without having access to code?
Okay, my bad. So you could have, so the thing is that AFL calculates like a hash of each block it covers, and it uses that it uses that information to figure out which blocks it has covered or which blocks it has not. If you want to know more, you would have to read the. So it would go beyond the time that Zaina has given me, but this is in terms like a simple explanation. So yeah, I hope that
Awesome.
gives you an idea. Yeah.
Also, for you, Jude, I posted in the chat a link to the technical white paper. There's a section there on coverage that will tell you how coverage is done. And I'll do one more question since we're low on time. There are two questions left, but we'll just choose one. One of them was about machine learning. I'll answer it real quick for you. There are machine learning applications in fuzzing. There are a few papers on it. If you want, you can message at Gokul in the Discord later. He probably knows of a few papers that do it. And the third
I'm not a pro in like machine learning, but yeah, I can try to answer. Yeah.
And the third one is, let's say if we have a black box software and we want to find a vulnerability in it, like Zoom or Chrome, how long on average does it take to get results?
I don't think, so I'm not sure if you would get any results as such if you try to fuzz Chrome or anything, because for targets like those, you would have to take, or it would be good to take like a part of it, or like say narrow down your testing to certain functions and then try to fuzz that. instead of fuzzing the whole binary or the whole program. So you could probably like look at, so there were like a lot of bugs being reported in the V8 engine, I think last year or the year back. So I mean, that's one way you could take up your target. And the other way is that if you're determined enough to take a very big target and work on it, you can. But the thing is that it's very important to narrow down where you're looking into. Otherwise, for such a large target, I mean, you would have to spend. I don't think you would get anything even after you spend a lot of time like fuzzing it, because Google is already fuzzing Chrome. Like it is like throwing, I think, more than 1,000 cores onto like just for Chrome. So it's like heavily fuzz, and I'm not sure. I don't think you would find a bug on Chrome, but for Zoom, maybe you can. Yeah, I've not. I mean, I've not looked into like targets like Zoom or anything. Yeah, but you could definitely do that.
I got a question and follow up for his Gokul. So would you say then that the potential time you could take to find a bug is proportional to how much people have fuzzed that software already?
Not exactly. So a lot of people can fuzz in any way they would like. What differs is that how you're approaching or how smart you're making your fuzzer. So it depends on, like as I said, seed is one factor. Then the function that you're trying to fuzz is another factor. So there are a lot of factors, which depends on the results that you may get. So it's just that, I mean, you could like say you could throw a fuzzer at it and say it might take a very long time to get your results. So the more cores you throw at it, the better results you get. So it's kind of hard to answer that question. Like it depends on a lot of stuff. So yeah, that's how it is.
Sweet. Thanks so much, Gokul. That was awesome.
Thank you so much.
All right, on to our fourth topic of 5. We'll now be moving to symbolic execution, which will be presented by Arvin, another PhD student and the most senior of the PhD students here. Symbolic execution was briefed in 2 of the earlier talks. Briefly, symbolic execution has become popular in the last decade. One of the most popular platforms for it, as you guys might laugh and guess, is Anger. You'll see symbolic execution used a lot in CTF challenges, especially for reverse engineering. But as we'll come to see, there are a lot of practical symbolic execution applications, as well as advancements to make symbolic execution better. All right, Arvin, take it away.
Thanks, Zion. I hope everybody can see the slide and also you can hear me fine. If you have any questions, you can post it on the chat on Twitch or on Zoom. I'll try to get to them at some point. So as Zion mentioned, my name is Arvin. I am a PhD student at CEFCOM. I occasionally play CTF with Shellfish, where I mostly do reverse engineering, but I'm also interested in more binary analysis stuff. Most of my current work is on making symbolic execution more widely usable. If you want to know more about me, that's my website. So before we talk about symbolic execution, I want to talk about software testing, which I'm guessing most people are aware of. Software testing's main objective is to verify if a program is working correctly or not. The most common technique is pretty simple and quick. You just run a program with a bunch of test cases and you check if the program is giving the output that you expect. One of the key challenges in software testing, and this is probably also true if you've done any assignments where you have to write more than like 500 lines of code, how do you know if you're testing all possible cases? Your challenge would be to create test cases which exhaustively test the entire program. And this task becomes significantly more difficult as the size of your program or the complexity of your program increases. While there are a lot of automated testing techniques like fuzzing, there are many more like property-based testing and things of that sort. they are not always accurate, or they are not necessarily always exhaustive. So symbolic execution was actually developed in the mid-70s to address this fundamental limitation of testing. The idea is that instead of executing with regular concrete values, you execute a program with symbolic values, and you track the operations that are performed on them. One of the main advantages of this approach is that you can explore multiple execution paths in a program instead of just one, which would be the case if you were running with any concrete inputs. And symbolic execution can exhaustively test the entire program, unlike regular testing, and is generally more accurate. Some of the popular tools for symbolic execution today are CLE, which works with source code, S2E, Anger, Manticore. They're all binary only symbolic execution tools. There are also more tools that are not there in this list, but these are the more commonly known ones. So let's dive in a little bit into symbolic execution to understand what actually happens, right? So everybody is familiar with concrete execution. This is a very simple flowchart of a program that checks if a number is odd or even. If you were, say, concretely executing this function, it would read a number, and let's say the number that's input is 2. Obviously, the yes branch is going to get satisfied, and so that branch is going to get executed, while the no branch and the odd block is not going to be executed. However, in symbolic execution, what happens is that when we hit that specific decision box and a branch happens, we end up exploring both paths simultaneously. So even the yes branch is explored and the no branch is also explored. Now, for a simple program like this, it doesn't seem very great because you just have 2 paths. But imagine if you have like a very big program that has like 10 paths, and then those paths give rise to even more branches and even more conditions, right? As the size increases, symbolic execution can end up exploring a lot of the program's execution paths and the program's CFG. So how does it actually work? So what happens is, instead of executing with concrete values, you execute with symbolic values, and you track the operations performed on them. Think of these symbolic values are more like variables that you are probably familiar from high school algebra, where you have an unknown and you have a bunch of equations and you need to find a value that kind of satisfies them, right? So that's one of the big differences. The other big difference is that we don't execute the program on bare metal, although there are some symbolic execution tools which do it, but usually the program is executed in a simulated / instrumented environment by the symbolic execution engine itself. One of the main things that happens, in addition to tracking how the symbolic values are operated and modified, whenever a branch happens, states get forked such that you end up following all the execution paths that would succeed after the branch is created. So if we go back to the previous slide, after this specific decision box here, we'll end up having 2 states, one which follows this specific branch and the other which follows the other specific branch. A third important thing that most of the symbolic execution tools do is, in addition to the fork, they also track the conditions that need to be satisfied so that this specific state is executed, and that is called as the path condition. So it will be a set of conditions which should be true, and in that case, execution will drive down that specific path. After this fork happens, the symbolic execution engine continues exploring all the paths until there are no more paths left to execute. So to get a better understanding of what actually happens when this specific decision block is hit, you end up executing the yes and the no. You would have 2 states that are created for both of them. For state 1, which is exploring this yes branch, your path condition would be that x mod 2 is 0. And for the no branch, the condition would be that x mod 2 is not equal to 0. In normal programs that are a little bit more complicated than this very simple, you can have hundreds, maybe sometimes even several thousands of conditions that need to be satisfied for a specific path constraint and for a specific path. So one of the things, if you've been following what I've said till now, you would realize that symbolic execution reasons about program execution and program inputs as a set of classes and not specific inputs. If you go back to this previous slide, you can see that execution would flow down this specific path for all inputs which satisfy this condition, which is execution would flow down this path for all even numbers. And similarly, on this side, execution would flow there for all the odd numbers. So that's how symbolic execution works. It reasons about classes of inputs as opposed to reasoning about specific concrete inputs. But however, when you have a specific bug that you want to debug, or when you want to generate a test case that you want to see, you want to actually try running a concrete test case, you obviously cannot give an entire set of classes and ask the program to do its job. So most symbolic execution tools, they use a third-party tool in order to derive an existing representative member of this specific set of classes. So you would solve the set of conditions, find one or maybe more values which satisfy those specific conditions. And this is achieved by using what are popularly called as SMT solvers. Some of the common examples are Z3 and CVC4. There are more that I have not listed here. These solvers, they accept an entire set of conditions and try to find a value for all the symbolic variables in those conditions, which would satisfy all of them. So if you go back to the previous slide, if you give this condition to an SMT solver and ask it to give you a value for X, it would probably return the value 4 or 8. Right? The exact value is usually random and depends on how the SMT tool works. SMT tools are based on a specific set of theories in computer logic or mathematical logic called satisfiability modulo theories, which define how, given a set of formula, can you determine if they can be satisfied or not. Not getting into more of this, if anybody's interested, you can always read about it. So now that we have an idea of what symbolic execution is, let's look at a quick demo to see what symbolic execution can do. So I'm going to demonstrate solving the Wyvern challenge from CSAW-CTF 2015 using Anger. This was a reversing challenge. If I remember correctly, I think it was a reversing 500 challenge. So I have the script already here. This script is there in Anger's example demos. I'll share the link after this. So there are a couple of Anger concepts here, which I am not going to discuss in great detail, but I'm going to point out the very important things. So if you remember, we said that we, instead of using concrete values, we use symbolic values. And that's actually what happens in the lines 18 and 19, which you see selected now. We are actually creating, we're actually asking Anger to create symbolic values instead of concrete values. And we feed this specific flag to the input of the program. Right, so this program, I shall quickly demo what actually happens. If you run this program, it asks you for a flag as input. You type something, say, oh, it's going to say you have failed. So clearly, it's somehow validating the input that we give, and it's going to say the answer is right or wrong. So we create a symbolic value, and we feed it to the standard input of the program. So a lot of the work has already been done before. I will not discuss into how we reverse engineered this program to find out that the key is 29 bytes long, or how the last byte is a new line. These are not directly related to symbolic execution. These are usually found by reversing the binary to find out what is going on. But we know that the last byte is, the first 28 bytes are neither null nor a new line, and the last byte has to be a new line, which is explicitly added here. So once we have set up all these constraints, we let symbolic execution do its trick here. So we just create we instantiate the symbolic execution engine. get it to run, and once it is finished running, it would find out the flag gets printed to the standard out of the program. I'm going to quickly show you by actually running the program. So while we're running this program, it's going to set up all the states, all the constraints, and so forth. What is actually happening is that it instantiates all the symbolic variables and continues executing through the entire program, trying to find out all the branches. And technically here, we just asked it to run. So it would explore all possible paths. And when that path terminates, it would just stop there. And one of those paths would have the answer. One of those paths would lead to the success. And then we can, once we find that specific path, we can ask the SMT solver to say, okay, this specific path was successful. Give me an input which would drive execution down this path. And that would be our answer. So you can see here, the program has finished and it has found the answer. This is actually the input that has to go to the program. We can verify by running this program again with this input. There we go. It says that it was successful and it has found the flag. I hope that made sense. The quick recap of what actually happened here. We reverse engineered the binary to get a very high level understanding of the behavior. We understood that it reads 29 bytes. The last byte is a new line, and it just prints out the flag after that. So we set up the std in to be symbolic values with specific conditions saying that the last byte is new line. None of the other bytes can be null or new lines. And then we let symbolic execution do its thing, and then finally we get the answer. We have absolutely no idea what validation is actually performed. The symbolic execution tool just handled all of it, and it just gave us the answer. This is just one of the many examples that are there for how to use Anger. This specific repository has a collection of a lot of scripts. There are also several CTF write-ups that you find online which demonstrate how Anger can be used to solve many different kinds of CTF challenges. But it's of course not very simple. It's not just simple CTF challenges like this that symbolic execution can do. It also can do more heavyweight things like actually finding bugs in programs, including finding security bugs. Gokul briefly mentioned that symbolic execution can be used to assist fuzzing to make it better, which is also another thing that happens. You can use multiple techniques together, try to get them to find an answer, find a bug, find a crash, make them run better, faster, things move faster. Symbolic execution is also commonly used to prove the correctness of a program. There is a closely related technique called symbolic model checking, which is very widely used in safety critical industries like the aviation industry, where they need to guarantee that the flight control software is going to work correctly because it's a very critical thing. So in those cases, they actually use symbolic model checking, which is very closely related to how symbolic execution works, to ensure that the program works as intended and is mostly bug-free. Symbolic execution is also used for reverse engineering tasks. Bill was talking earlier about how control flow graphs need to be generated automatically. Anger actually has one specific technique for generating control flow graphs using symbolic execution. Ashwin briefly mentioned how symbolic execution can be used for deobfuscating binaries. One specific case where symbolic execution shines is in dealing with opaque predicates. As Ashwin mentioned, the program is written in such a way that it's not obvious what the execution path is, but there is only one specific execution path. Symbolic execution can quickly explore and determine which is the path that is feasible while discarding all of the other infeasible paths, and thus opaque predicates are some of the deobfuscation techniques that symbolic execution can do. But as you mentioned, it's not a foolproof method. There are still some techniques that symbolic execution cannot handle. Symbolic execution is also extensively used to generate exploits automatically. We have a project called Rex within Anger, which we actually use for generating exploits, and that relies a good extent on symbolic execution. There are probably even more applications that I'm not aware of which symbolic execution can do, but hopefully this gives you an idea that this is something that really can do a lot of things. So one question that you might be asking is, okay, it does a lot of things. You say that it can find bugs, it can exhaustively and accurately analyze programs. So then why do we still have bugs? It's all great. Unfortunately, symbolic execution has a lot of problems. It suffers from speed issues. It's very slow because it's interpreted in nature, and because it uses intermediate representations, which is briefly mentioned in Will's talk. It actually uses intermediate representation so that it can accurately analyze program execution and capture all of the effects exhaustively, and that makes it really slow. It also does not scale very well. Most modern programs have several 100,000, maybe millions of lines, and there are execution paths that will crisscross across the program. And when you add libraries into the mix, it's just going to have so many execution paths that is probably not going to scale to most modern programs. That is why fuzzing is still the most widely used technique for finding security bugs today. When compared to symbolic execution, it's used way more faster and more commonly. There is also another aspect to symbolic execution. There are not very many easy to use tools in order to analyze programs using symbolic execution. Unlike fuzzing, if you check out AFL, it's very easy to get started and get doing something. But most existing tools, you have a very steep learning curve, and it's also very difficult to know what capabilities they have and what's actually happening so that you can interact and understand it better. But we are actually working on some of these things at ASU, at CEFCOM. We are actually doing core research, which is coming up with ways to speed up symbolic execution and scale it to larger code bases like web browsers. Quite ambitious, but we'll see how it happens. That is a lot of the work that I am working on right now. There are others in our lab who are working on a more human-focused aspect of symbolic execution. Can we build better tooling so that developers can actually get up to speed faster and actually make more use of symbolic execution and integrate it into their dev workflow and get a lot of things happening? There is a lot of scope for a lot of applied work of symbolic execution. Can we use symbolic execution to solve some specific challenges or problems today? If you're interested in any of this, feel free to get into touch with any of our professors or even one of us. And if there's something that you like, we can probably figure something out and get something done. So in summary, symbolic execution is a technique that can explore all possible execution paths through a program. This is achieved by using symbolic values instead of concrete inputs to sort of explore through the program's execution path. As we've seen that there are a wide variety of problems that symbolic execution can be applied to, but however, it does not scale very well to a lot of large programs and can be quite slow and challenging to use effectively. So thank you. That's all I had to say about symbolic execution. I'll be happy to take any questions on Zoom or on Twitch.
Awesome. We got time for maybe 2 questions. So if you have any questions, bring them.
All right, we have a question here on Zoom. It says, I thought symbolic model checking would guarantee up to a no runtime errors level and not functional correctness reserved to theorem provers and proof assistants. If you have any resources for this, I'd be interested in this. So I don't work on model checking. I am actually not at all familiar with model checking. I know it exists. I know it's very related to symbolic execution, but I absolutely have no idea of what model checking is. There are a lot of people who work on it. If you're interested, you can explore a lot of the work that I think the INRIA lab in Europe does. I think they do a lot of model checking stuff, but I have absolutely no idea about it. Sorry.
Any other questions from Twitch?
I guess not.
Yeah, I guess not. Well, if you guys haven't, go check out Anger, as it's been mentioned many times in these presentations. Great place for symbolic execution. Thank you so much, Arvind. Awesome. All right, and now we are on to the final talk of the night. by Kyle. Kylebot is known as one of the best pwners on Shellfish. He does a lot of CTFing. He may CTF more than anybody, and he has a specialty research area of exploitation in Linux kernel or just kernels in general. Kernels make up some of the most fundamental pieces of all of computers, and Kyle is here to talk about how exactly you can exploit them, why it's cool, and some future work that happens in academia. All right, Kyle, take it away.
Thank you, Zion, for the introduction. So can you hear me and see my slides?
Yep, looks good.
Thank you. So today I'm going to give a talk about the Linux kernel exploitation, but an introductory one. First of all, I'd like to introduce myself. So I'm Kylebot. If you're on the our Discord, you can use this handle to find me. And I'm also an ASU PhD student at CEFCON as well. And I'm a member of Shellfish Hacking Group or a CTF team. As Zion said, I play CTF a lot. And also my research focus on kernel security and browser security and some other program analysis fields, for example, fuzzing and symbolic execution. So let's get started. First of all, what is a kernel? So kernel is actually also a piece of program, and it handles whatever you are doing on the user level applications. For example, your Twitter, your Facebook app, whatever apps you use, and it's an agent between those programs and those hardware devices. For example, CPU, memory, disks, devices, all kinds of devices like camera, sensors, and mouses, keyboards, etc. So since it's managing all the devices and interactions with softwares, of course, it's used everywhere and also important. So currently, all major operating systems have a kernel. Mac OS, Windows, Linux, and other operating systems like FreeBSD and other stuff, they all have a kernel. And all phones, desktops, and tablets, they all have an operating system. So also they have kernels. Since kernels are managing all those interactions between softwares and hardwares, they are, of course, important, right? So for example, if everybody has a phone, and probably about half of people are having Android phones. An Android operating system uses Linux kernel as Android operating system uses Linux kernel as the internal core to managing hardwares. So of course, Linux kernel security is very essential to billions of users. And also, all the current supercomputers uses the Linux computer because it's super fast speed. And supercomputers, as everybody knows, contains all those important research data. If there is one person finds and all those supercomputers are shared by different research groups. If there is one malicious researcher using a supercomputer and he happens to have a Linux kernel vulnerability and use that vulnerability to obtain all the important research data on that supercomputer, that will be a disaster to other research groups. And also, Linux kernel is powering a large number of Internet of Things or IoT devices. Think about it. A lot of people have routers, have those smart assistants like Echo, like those speakers in your home or cameras in your home or in your bedroom. If someone can attack your Linux kernel and control all the hardwares, they probably can monitor your bedroom through the camera, or eavesdropping all your messages with other on the internet through the router, which is a disaster. And that's why Linux kernel security is very important. So let's talk about the landscape of Linux kernel security at this moment. So in Linux kernel security, the goal is quite different from the program analysis right now. The program analysis usually help you to understand software. And here we're targeting a single piece of software. We try to prevent user privacy intrusion by protecting this important software. And for example, we prevent in Linux kernel security, we prevent secret camera monitoring, as I talked about before. We also, by securing those, for example, phones, smart assistant, you can prevent conversation eavesdropping, and also keyloggers by preventing somebody stealing your password remotely when you're typing your password on a website. Also, so in Linux kernel security, we use different approaches to finding vulnerabilities before bad guys find them. For example, all those techniques talked about before this talk, for example, fuzzing, static analysis, symbolic execution, we use all of them to find vulnerabilities in Linux kernel. We also use bug bounty. Some companies, for example, Google, are offering a bug bounty for whoever finds vulnerabilities in Linux kernel. And to make exploitation harder, Linux kernel introduces a lot of hardenings to it by reducing attack surfaces. By this is through restricting how users can interact with the kernel. For example, using a second filter or through a container. I believe some of you have heard of Docker, which is one of the way to harden Linux kernel to protect Linux kernel. Also, there are other various protections to break attack chains. If you know how to exploit programs, kernel is no different from the normal user space program. You need a primitive first and go through an attack chain to achieve your attack goal. There are a lot of hardenings, a lot of protections in Linux kernel to break those attack chains so that no attack can be successfully performed. So Linux kernel exploitation is actually in everyday's life, in everybody's life. And for example, jailbreaking is a very good example of Linux kernel exploitation. As you can see, this is a very cool output. If you try to jailbreak your phone, you probably will see something similar. And then after that, you will have full control over your phone. You can install whatever program you want on it. You can unlock your phone. You can just do anything you want, which is good, right? Probably not. That means jailbreaking is exploiting vulnerabilities in Linux kernel. If you can do jailbreaking with jailbreak toolkits, that means attackers can also do that. If you jailbreak your Linux kernel and stay the same version, it's leaving a backdoor to potential attackers. They can follow your footprint and using the same attack to gain control over your phone. So I believe some of you know the exploitation part of in user space. The goal of kernel exploitation is a little bit from user space exploitation, which is to gain remote code execution. In Linux kernel, or in generally in kernel space, what you want to do is to escalate your privilege from normal users to root. Imagine a case you someday a friend comes to your home and he wants to use something urgent to do something urgent, and he wants to use your computer, but you have something very sensitive or important in your computer. You don't want other people to know. So you open up a guest account for the friend, but this friend is malicious, it's an attacker. He download an exploit and exploit your computer. Then he will get root privilege or administrator privilege in Windows terminology. He will have access to all the content on your computer. So we'll briefly talk about how Linux kernel exploitation is done. In Linux, or generally say in computers, we have user space program and kernel space, which is where kernel resides. They are actually in the same memory. They are just separated by a boundary set by kernel. And the kernel itself is no different from user space program. You can think that your program is running in a room, which is called user space, and the kernel is running in another room in kernel space, and you're exchanging messages through a hole on the wall. And that's how computers work. But this important software has vulnerabilities too. In user space, you will see some segmentation faults if you write low-level language programs like C or C++. You see them very often, right? In kernel, it has its own terminology. It's called panic. It has all those vulnerabilities that user program can have. For example, use after free, double free, heap overflow, stack overflow, all kinds of those stuff. And because kernel space or kernels are so complicated, they also have their own vulnerability categories, such as double fetch, ref count bugs. But other than that, the exploitation strategies are just the same. You can use shellcode. After you gain control, you can jump to your shellcode or use return-oriented programming or ROP to hijack the control flow in Linux kernel. And then you can call kernel functions to escalate your privilege from user space to from user to root to gain control to the on the computer. All right. So these two are the most common exploitation strategies. As I said, you can do shellcode and ROP, right? So in Linux kernel, there is a terminology for jumping to shellcode type of exploitation. It's called return to user. So the exploitation strategy goes like this. In user space, because it's basically two programs running at in the same memory, right? You can allocate a memory mapping and store your shellcode inside user space, and then you trigger a vulnerability in kernel space and tells the kernel, hey, I want to jump to that specific mapping, and then you gain control over kernel because kernel is executing your shellcode. Well, since this exploitation is so simple, the hardware vendors and Linux kernel developers has been implementing different kinds of protections to kill this exploitation method. The most famous one is SMEP. Or supervisor mode execution prevention in the full form. And so return to user has been killed. Then the first smart exploit developers invented another technique called return to directory or return to dir. It's kind of different by using the similar idea. Instead of putting your shellcode inside user space, they put shellcode inside kernel space through some smart memory manipulation. So it's still similar, but the kernel is the user or the attacker is putting their controlled shellcode inside kernel space through some magically syscall manipulation. But then later, this technique has been killed by Intel too through a SMAP. They basically stop execution from kernel space. Sorry, shellcode execution from user space. They specifically mapped those regions that can be controlled by user as non-executable, so you just can't jump to your shellcode, although it is in kernel space. Although this attack has been killed, it's actually still a step to bypass SMAP in modern Linux kernel exploitation. Actually, I'm using it daily to bypass SMAP in my current research. So we briefly talked about what is the Linux kernel and what is the Linux kernel exploitation. What can we do research on Linux kernel? So for example, Linux kernel is a super complicated software. It's very hard to find bugs in it. So how to automatically find bugs in Linux kernel is still a hot topic. For example, in previous fuzzing section, Gokul mentioned that fuzzing is the way that people are using to automatically find bugs in softwares. But Linux kernel is a little bit different. Linux kernel is more complicated in user space programs. It does not just parse programs. It has a very super complicated state transition. And how to capture those state transition in Linux kernel is still a open question. There are also other opportunities, like how to automatically evaluate the severities of found bugs and identify those exploitable security vulnerabilities. There are tons of bugs, off by one, access of invalid memories, but use after free and double free, those vulnerabilities are more critical to developers. They just want to fix them as soon as possible when they are discovered. So how to prioritize, how to evaluate the severities of found bugs and fix those critical vulnerabilities as soon as possible is still a research question, and it's still open. Also, from defenders' side, they want to identify Linux kernel exploitation attempts, either successfully or failed attempts. In big organizations, they have those very sensitive data. They have user information, credit card information. They tend to become targets of malicious attackers. It's very common that Linux kernel exploitation has been deployed on their servers to gain server controls. So if there is a method to automatically identify those attempts and then notify defenders to shut down the server or deploy a patch as soon as possible, it will be very good for the company's security. But still, we don't have a very good technology to do that automatically. Also, Linux kernel is so complicated. The exploit reliability is still an issue. So how to improve Linux kernel exploit reliability is still a question, which is also my current research project. And also we talk about many protections in Linux kernel, how to bypass those protections and find vulnerable weak point in Linux kernel, and then inform Linux kernel developers to fix those weak points. It also is also a research opportunity. Although it sounds like what attackers do, but it's called offensive security. We find weak point in important softwares and let the developers fix those weak points before attackers start exploiting them. So I want to talk about some fun things, like why do we need to care about why do we want to learn Linux kernel exploitation? So for fun and to find bugs, of course, for finding bugs before bad guys and securing machines all over the world, basically save the world. Not really. At least you can say to a friend, your phone has my code running in it. Isn't that interesting? And also for fame, because Linux kernel is so hard to exploit, and it's so complicated, and because of all kinds of protections. If you can bypass all the protections and exploit it, you can get fame. And also money. As you can see here, there are a lot of reward programs. As long as you can find exploitable bugs or denial of service bugs in Linux kernel, you'll get money, a lot of it. And also you can use it to DOS your opponent team's machines during some CTFs or classes. I believe some of the speakers today were the victims of this category. All right, let's show some demo. But I'm not sure whether I can do it, but let me check. Great. So there was a network issue right before this talk, and I urgently talked with our network maintainers. Now it's fixed. Let me demo my Linux kernel exploitation. All right, share my screen. All right. Oh no. Can you see my terminal right now?
Yep.
Make this.
Or well, sorry, now we can.
This?
Now we can. We're good. Yeah.
Okay,
good.
great. Okay, I prepared a demo, which is a real world CVE from a few years back. It's still relevant though, those techniques used in this exploitation. So because kernel is kind of delicate, I don't want to mess up my current setup. I'm going to do it in a VM. As you can see, this is a Debian operating system using Linux kernel. Yeah, just like normal users, normal setup. I wrote this exploit a few yesterday, and I'm going to run it. Hopefully, we can get a root shell. So, okay, right now, inside this virtual machine, I am a normal user. As you can see, my ID is just 1,000. I'm normal user. I cannot do any privileged operations, like for example, cat et configuration shadow. It's just I can't. I'm a normal user. Oh, what happen if you run this program? Oh, it's doing something. You know, Linux kernel exploitation is kind of hard. Oh, now we get a shell. We are dropped into another shell, but this time it's a little bit different. For root or UID 0, now we can do whatever privileged operations on this computer. We can just do cat etc shadow, and we can do it. And we can change password and override, mess up all the file systems like this. You know, don't do this, but this is just a demonstration, right? Password, and then you will be overwritten. Yes, this is the demonstration. Okay, let's kill it and go through the exploit a little bit. Hopefully I can explain it. So in this exploit, I'm using the most common exploitation technique, which is a return to user that I explained earlier. I just mapped the shellcode into the I mapped the shellcode into user space and then jump to user space shellcode. And as you can see, I basically trigger a vulnerability in Linux kernel and then let kernel to execute this this shellcode for me. It tells the kernel to prepare a root credential for me and then commit this credential to my current process. after that, I just simply return back to user space because I mess up something. I had the user space program will crash, so I set up a signal handler to handle the segmentation fault. And then inside the signal handler, we will become root user. And yeah, that's about it. That's the end of the demo. I will stop sharing and go back to the slides. All right. So we just finished a demonstration of a real world exploitation. And in today's talk, we'll talk about Linux kernel, which is a important software behind many devices, and it's very popular. So its security is very important. There are a lot of research opportunities in Linux kernel exploitation, as we talked about before. And since it's just one single binary, we can apply all the techniques, program analysis techniques in the previous talks on this Linux kernel to discover new primitives or new vulnerabilities. And then, of course, the exploitation itself is fun and rewarding. Now, feel free to shoot any questions.
All right, we'll be taking questions for Kyle on the SICK kernel exploitation, also from Twitch as well. All right, we got a long one in Twitch. Do you have to thoroughly understand the whole Linux kernel source code to exploit it? Because it's like tens of millions of lines and it keeps growing. How do you effectively target the vulnerability in the Linux internals and set the stop loss points for beginners? So I guess how do beginners start exploiting the Linux kernel when there's so much code?
This is actually a good question. So I feel intimidated when I started learning Linux kernel exploitation as well. But actually, it's not that bad. It has a lot of code in it, but most of them is just irrelevant. For a attack chain to work, you simply need to understand the functions in the attack chain. And after you just, for example, there are 200 something system calls in Linux kernel, but for a exploitation to work, you probably only need to learn 10, probably 20 at most of them. And you don't need to understand the source code, every piece of source code of those functions. You just need to know how to use it. And you only fully understand the function that the vulnerability is in. And that's it. And also, there are a lot of blogs talking about how to attack the kernel. You simply need to understand those attacks, which is a linear attack chain. You understand those, apply those attack chains onto your vulnerability, and you can get a shell.
We got some other ones in Zoom. Sean asks, where do you learn and practice kernel exploitation? I guess that's kind of related.
Oh, so this is a good question. Linux kernel exploitation is intimidating, as I said, but you can start with some simple questions or simple challenges like CTF challenges. They have very easy vulnerable kernel modules. Consists of probably 60 or 50 lines of code. If you can exploit those vulnerable drivers, you can use the same technique to exploit Linux kernel, because Linux kernel drivers are in the same space as the core of Linux kernel. So learn them first, start learning them first, and understand the APIs, and then start doing exploitation in the core kernel.
Awesome. Jude asks, do you have to access kernel space to do kernel exploits?
Yes. So you have to have access to kernel space to do kernel exploits. So I'm not sure what you mean by kernel access here.
I think he might.
I will explain the.
I was gonna say, I think he might be asking, like, how do you get to the kernel? Like, how does a normal program access the kernel?
So there are a lot of ways to get access to kernel space. Whenever you, for example, whenever you are issuing a syscall, or let's say in C program, you use a command printf. It's actually the library is actually using printf, using a write syscall underlying printf to communicate with kernel. If you find a vulnerability in the write syscall, and the vulnerability itself will be triggered in kernel space. I'm not sure whether that answers your question.
I think that did. I think that was pretty good. And I think
cool.
Yeah, I think that's all we got. Thank you, Kyle.
Thank you for having me.
Awesome.
All right, I'll stop sharing. Thank you, Zion.
Yeah. All right, guys, that is it. That is our fifth and final speaker. We really hope you guys enjoyed this kind of litany of research in binary analysis and the kind of modern things that are happening in research to make the world safer. If you have questions for any of the speakers today, your best bet is to get onto the ASU Hacking Club Discord, which you can find from our website link. If you're in the Zoom, of course, you're already there. You can ping them. They're all listed as who did what talk, and you can ping them there. And that's about it. If you guys have any other questions, feel free to put it in the chat. We'll keep this open for about 10 minutes. And that's it. Thank you for coming. And thank you, speakers.
Awesome. Thanks for having us.